Hi, thanks for being here. Like he said, my name is Lance. I'm a machine learning engineer at Box. And I'm here to talk to you about a construct we built at Box that helped us increase our velocity by modularizing our machine learning jobs. Yeah, so a little about me. I'm a member of the machine learning team at Box. Primarily, I'm the designer and sort of babysitter of the machine learning infrastructure. I have an MS and BS from Duke University, mostly specializing in distributed systems and machine learning. So, machine learning at Box. So at Box, overall, our goal is to make it ridiculously easy to share, access, and manage your content. And machine learning plays a pretty big part in that. First of all, in terms of security, one of the big things we do with machine learning at Box is figuring out whether a document you uploaded to Box is confidential or not. And based on this, we can tell you whether your access permissions are too high or too low on the document. You can imagine there's all sorts of defenses against malicious attackers and whatnot that we build as well. The next big thing we have is recommendations. Just like any other engine you use online, helps you navigate through Box easily and find your content. And in relation to that, search relevancy to boost relevance for files per user. So just to switch context a bit, here to give you the basic anatomy of an ML job. So let's put ourselves in the shoes of a data engineer. You wake up today and you say, hey, I'm going to write my machine learning job. The first thing you might want to do is you want to read and parse data from your multiple sources. You parse data, you take the data out, you convert it to specific data types that makes the rest of the computation easier. The next thing you might want to do is you want to collate the data. So you read data from multiple sources. You might want to do a couple joins. You want to dedupe your data sets and whatnot. Next up, you might want to do some sort of feature massaging, i.e. you want to drop certain columns that you might not need for this computation. Let's say you want to compute the z-score for a certain column, normalize it somehow, transform, augment your features. Anything you want to do to make it palatable to be consumed by your machine learning algorithm. And obviously next, you run your core algorithm, whether it be regression, classification, clustering, any topic modeling. However it is, you run your algorithm, spits out a result, and now you want to compute your metrics. So maybe if you did regression, you're computing the area under the curve. If you did some sort of classification, you want to do some binary or multi-class metrics. Whatever it is, you do metrics. Yeah, at the end of the day, you're happy with your algorithm. You say, hey, I want to write my results for my downstream consumers to use. You write it to an external database, to a public API, whatever it is. So in general, most your machine learning or data processing jobs will have these 6 steps. And really, the question is, how do you use this knowledge to make writing machine learning jobs better? So at Box, we introduced this notion called sparkles, endearingly. So in our world, a sparkle is a single logical unit of work. It's basically comprised of a series of Spark actions or transformations that do one specific thing. And overall, this construct of sparkles enforces type safety, modularity, testability, gives a standard way to do metrics and logging, and enforces best Spark programming practices, which we'll get to later. So the usage. Back to our situation. You wake up this morning, and your task for yourself is, hey, I want to write a label propagation algorithm using sparkles. So here's an example of how you would do it using sparkles. So the first thing you want to do is you want to take the read text file sparkles that contains all sorts of nice configurations to read from whatever database. You feed in your text path, and you get an RDD of string that you pulled out of that data source. Next, you might have something stored in a Hadoop sequence file. And so you have read sequence file. You pass in the path, you get an RDD of B. Next thing you might want to do is your RDD of A that you read earlier is of type string or is type JSON. And eventually, you want to convert it to some type A that you want to use for the rest of your calculation. So you JSON decode that. You take JSON decode Sparkle. You feed it RDD of A, and you get RDD of C in return. Same thing you want to do with the sequence file output you read earlier. You want to decode it to type A. You now have these 2 RDDs, RDDC and RDDD. Let's say you want to join by key. You take the join by key Sparkle. It figures out a bunch of logistics for you and eventually just joins your 2 RDDs for you. You get your RDDE. And one of the more common things you might want to do is to take a global set of indices or IDs and convert it to an index that goes from 1 to n. So you're just localizing the IDs. You take RDDE and you feed it into localized Sparkle. And localized Sparkle happily takes your global IDs and writes them into 1 to n for you. Finally, you're done with all your data massaging and cleaning, and you're happy to do label propagation. So label propagation, you have a bunch of data points and a very sparse set of tags spread across your data points, and you want to spread those tags across your data points. So you take your RDD of f that's been localized, you feed it into your label propagation, and you get some RDD of g back, the result of label propagation. You're happy with that. Now you want to do some metrics. Accuracy metric next. You take your RDD of g, you feed it into a set of sparkles that know, in general, how to compute accuracies. Computes accuracy for you, spits out RDD of h, and you're happy. Finally, you're done. You want to take those local indices and convert it back to global, just so you can reference it in like whatever global database you've been using. And you feed RDD of h in globalized Sparkle, and you get RDD of I. Results are done. Now you want to write it to metadata. You take metadata Sparkle, you write it into, it writes to metadata for you and writes to HDFS. So yes, this is your label propagation algorithm written in terms of Sparkles. So we would hope that by sort of viewing it, you can easily see what's going on. You can see every single step. You can see which parts of the logic is doing what work. It's very readable, composable, and easy to understand. So I guess you compare this Spark job to a normal Spark job that you would see. So compare this with a series of maps, filters, joins, cogroups. I think most would argue that this is very readable, easy to understand, and reusable. Cool. So we step back a little to talk about the design of Sparkles. The goal of Sparkles is to be able to compose modules of Spark computation. Secondly, we want to be able to provide a very nice surfaced syntax so it reads beautifully. And finally, we want to leverage the type system to enforce inputs and outputs between Sparkles. So just the high level, composing in the functional programming world, easily implemented as a flat map. So given any Sparkle A, and if you get a function that goes from A to Sparkle of B, you get a flat map, and it easily allows you to compose a Sparkle. Nice surface syntax is provided by the for comprehension, as we saw in the previous slide. And to leverage a type system, in the end of the day, the Sparkle is just a function with some sprinkles on top. So specific implementation, what is a Sparkle? So a Sparkle is a, like I said, single logical unit of work in Spark that produces an output result of A. So trait Sparkle of type A. Every Sparkle has its base method. It's just a run method. It's a very simple function that takes a Spark context, does its work, and spits out output of type A. A Sparkle will also have flat map. This is what allows us to do the very nice for comprehension. And what flat map does is it gives you a new Sparkle, where in the run method, all it does is it triggers run on all the parent Sparkles that it's had in the chain, takes that result, applies it on the function that you've provided. So this is f of A to Sparkle of B, and triggers run on those succeeding Sparkles. In the for comprehension world, this f, I suppose, is the subsequent sort of Sparkles that come after. So yeah, when you do a flat map between Sparkles, it gives you a new one, wherein the run just chains together, runs the Sparkles before it, and runs the Sparkles after it, and nicely feeds in the result. Naturally, there's also a map. So at the end of your for comprehension, you want to yield a result. You have an f that goes from A to B. So do a map, you get a Sparkle of B, and the run method just runs the parent Sparkles and just feeds it into the function you give it to yield whatever result. Yeah. So in the end of the day, at its very core, we've added a lot of extra methods, but the three core methods that makes the Sparkle what it is these three. The Sparkle has a run method, a flat map, and a map. So it's fairly simple. A Sparkle is just a function that requires a Spark context and produces some value of A. And we compose Sparkles using flat map and map. But this detail is oftenly like syntactically hidden via the four comprehensions that we saw earlier. Cool. One thing you might want to ask is, how do sparkles take additional arguments? And this is an example of a sparkle, or the shell of a sparkle. And the answer to that is these additional arguments can be fed as constructor arguments to the sparkle. So in this case, JSON decode sparkle decodes a JSON into a specific type T. So the run method will have access to the JSON RDD that you feed in the constructor argument. And just as a tangent, this is how most languages support closures. Cool. So bird's eye view, the anatomy of a sparkle. First of all, it has its constructor arguments as the function arguments to the sparkle. You have a run method. It takes the Spark context and spits out an output Z. And that output Z is the type of that sparkle. Cool. On to the benefits. So we saw the code. So high-level benefits. First of all, we achieve very nice type safety between sparkles. So again, let's look at a for comprehension. You have one sparkle, or some sparkle. The output of some sparkle is fed into yet another sparkle. And the output of yet another sparkle is, another sparkle. And the output of that is fed into yet another sparkle. It's a chain in the end of the day. So you can see that the output of some sparkle fed into another sparkle, compiler types checks that, of course, and makes sure that the type output of some sparkle is the input of another sparkle, so they match. And in the same way, the output of another sparkle fed into yet another sparkle types checks as well. So you sort of make sure that at compile time, you can catch like any type errors, and it's given to you in a nice chain, as shown. Secondly, we have modularity with sparkles. This one is a fairly obvious point. Each one of the sparkles has a specific action or a specific responsibility, and it does just that. And then you chain them together, or you piece them together like a puzzle to build your machine learning algorithm. Next, testing with sparkles is fairly easy as well and nice. Because all the dependencies are fed in either through the run method or through the constructor, you can imagine it's very easy to mock this. So you can mock a Spark context and feed it into the run method and do all sorts of testing. And in the same way, you can mock any inputs to your function through the constructor and run your test that way. Finally, we have a standardized way of doing metrics and logging with Sparkle. Most of you might be familiar with this, as it's called the template method. So anyone implementing a Sparkle will implement the run method. But under the hood, before we trigger the run method, there's a bunch of arbitrary things we can call. So in our use case, we can log things like, declare to the world that this Sparkle is running now, collect a bunch of useful metrics like, RDD partitions, like resource consumption and whatnot, before we trigger a run. And then after that, collect the same metrics and do the same logging. And all of this comes for free if you implement the Sparkle. And lastly, you get good code with Sparkles. You can imagine there's many different ways, logical ways to write a specific task. And so in general, once you've figured out a nice Spark good practices way to do things, you put it in a Sparkle and it's reusable. And anyone who uses that Sparkle will be able to take advantage of your good Spark programming code. That's it. So summary, overall, Sparkles, we believe, provides a very natural way of thinking of Spark work. At Box, it has helped us increase their velocity with modularity and its dryness. It helps us reduce programmatic errors with type safety when you're chaining together sparkles and with testability. And helped us enforce best practices programming. And finally, it helps us standardize our metrics and logging. That's about time for me. Thank you.
You can stay here. So we do have a 15-minute break that starts right now. But if people would like to go get a cup of coffee during this 15-minute break, can do so quietly, we'll take a couple of questions for Lance that will eat into your break. So make your choice. If you have some questions, feel free. And then we'll see some of you back in 15 minutes. Any questions for Lance? Would you mind using one of the microphones? There's a microphone at a podium. Just because we have a live stream to take care of. It won't come to you, though, so you'll have to go to it.
I have a question. So a Sparkle is effectively an interface that has one method run, and it takes like a couple of constructor parameters. And it sounds like a lot like a function to me. Like, so what's the, like, I mean, obviously the flat map gives you this syntactical sugar of doing the for comprehension. Are there any other benefits of, like, versus just having a library of functions that take an input type or several inputs, and that would also be type safe in a language like Scala? And what other benefits do you see of Sparkles there?
Yeah, so we went through a lot of the benefits, but you're right. Essentially, at its core, it's a function. That's what allows us to do all the niceties. But like I mentioned, we've built a lot of sort of metrics and logging around the Sparkle. So coming with a Sparkle trait, you have the 3 base methods, like you mentioned, run, map, and flat map. But there's other things like how we collect metrics, how we do logging, all built in for you. But so you're right.
Instrumentation basically is.
Pretty much, exactly, yeah. Thank you.
I have 2 questions. Are you open sourcing this? First one? Huh?
Yes, we're working to clean up our Sparkle libraries, and we'll push it open source very soon, yeah.
Good, thanks. The other question is, in the light of the data frames API and the ML pipelines that is coming up, kind of the same stuff. Some of the targets that you are trying to achieve are going to be achieved with those stuff. So how do you see this transition to that? Will you be updating this to utilize those features, or how do you see this going forward?
Right. So you certainly touched on one of the key things that we've been actively thinking of. What happens when you have optimizations across Sparkles? So data frames is a very big thing, but even things like, which RDDs to persist and like how you manage this in memory. So this is like something we're actively building. So one thing we've introduced, we call it Sparkle metadata, and it allows the Sparkle to be aware of like the job and other things in its surrounding. But yes, we're actively thinking of this if we can go through certain points later on offline. But in general, this is something we're thinking of, yeah.
Thank you.
Thanks.
All right, let's thank Lance.